Alright, so let's look at this problem. Again, we're constructing the shear force and the bending moment diagram for this beam. The first thing we want to do is actually find our reactions here at A. So what I'm going to do is I'm going to assume that I have a force at A acting up and a moment at A. And we're not going to worry about the axial force. We're not drawing an axial force diagram, and it shouldn't have any role in our system. So to find these reactions, I'm going to want to probably take this distributed load and, for reaction purposes, find a concentrated equivalent. So what's the concentrated equivalent force for this? Basically the area under the graph. So it has a base of 12 and a height of 4, so that should be a 48 kip force. And what's the distance from the fixed connection? Yeah, half the distance, or 6 feet. So with all that information, I should be able to find my reactions. So I'm going to do my statics. I'm going to assume right-hand rule for my sign convention, and I'm going to sum moments at A. That's a good place to start because AY will create no moment at A, and I should be able to solve for the reaction moment. So about A, with my sign convention, right-hand rule, what kind of moment is this? Positive or negative? Negative. About A, my concentrated equivalent force of 48 kips. Does that create positive or negative moment? Negative. And what's the moment arm of that? 6 feet. And then I have this 60 kip force way out here on the end. Does that create positive or negative moment? Negative again. And the moment arm for that is, let's make that 8 feet. Sorry about that. Needed a dimension. So that would be a total of 20 feet. And then way out here on the end is our 100 kip foot moment. And with this sign convention, is that positive or negative? Negative. So all of our units are the same, so we should be able to solve for the moment at A. It looks negative. You guys are going to have to help me with that. It's going to be a pretty big number. 1588? Anybody else get that? Great. Now you'll notice that I assumed this to be a positive bending moment because I knew I was going to draw a bending moment diagram, but we can see that the value is going to be a negative bending moment. And then the last reaction would be the force there. So I'll sum forces in the y direction. And let's see, I just have AY acting up. That's my only unknown. I've got the concentrated equivalent acting down, 48 and 60. So it looks like AY is 108. Any questions about that? So now let's make our template. So there's my right side, or my left side and my right side. Something's probably going to happen here as I go from a continuous force to not, or a different one, so I'll put that in as a point of interest. And I think that's really all I need right now. I may generate another one later, I'm not sure. Let's see. So let's do our shear diagram first. Establish positive X and shear values. Our shear will be in kips. So starting at the left-hand side, what is the shear at A? Well, we got a reaction of 108 and it's up, so that's a positive shear, right? Of 108. What's the shear out here at the free end? if you took this little chunk and kind of did a little free body that's very small just to the left of the 60 kip force, and assume that for us positive shear force is up on that face, right? And if you look at the equilibrium there, what would the shear force be equal to? 60. Would it be positive or negative? Positive. So we're probably going to then hit, we better hit a 60 on that side. Okay, so let's use our relationships. We know that the change in shear between any 2 points is the area under the load diagram, and that the slope of the shear diagram is the force. So here's a good place where we have a nice continuous load over the first 12 feet. So over the first 12 feet, the area under the load curve is what? Base times height, 48. And it's negative because the force is down. So if I start at 108 and subtract 48, what do I get? 60. And what's the shape of the curve between those 2 points? Well, it's given by the load. And the load is constant and negative. So there's a constant negative slope. And again, if you looked at the slope value there, it'd be 1 to minus 4. So we have kind of a trapezoidal shaped shear over the first 12 feet. Now the change in shear between these 2 points, according to our definition, is the area of the load curve. And what's the load over the last 8 feet? 0. So no change. So 60 to 60. And the slope of the curve between those points, given by the load, and the load is 0. So there's our 0 slope, horizontal line. So the last 8 feet has a constant shear of positive 60. Okay? So the next step is to draw our moment diagram. So again, positive x-axis, positive moment, and all these will have values of kip feet. Let's see what we know. What is the bending moment on the left-hand side? Which should be our moment, which we found to be negative 1588. So we're going to start off at minus 1588. Normally on a free end we would know the moment is 0, but in this particular problem there's an applied moment of 100. And what kind of bending moment is that? Positive or negative? Negative. So I should end up at negative 100.
That's going to be, it's going to change, like, it's going to be a positive change then, right?
It would have to be, right? Because we're going from a fairly large negative value to a smaller negative value. So the change in moment is going to be positive. Let's see if that works out. We know that our change in moment is the area under the shear diagram. And what's the area under the shear diagram? It's all positive. So it will be a positive change. And then the slope of our moment diagram will be given by the shear. So let's start with this first chunk here over the first 12 feet. What's the area under this part of the curve? It's a trapezoid. So area of a trapezoid is you average the height times the base. So the average of the height is, what is that? That's 54 and 30, 84. So what's 84 times 12? 1,008. So we're going to add 1,008, and that should bring us to something like 5 580, right? 1588 plus 1008 gets us to 580. What's the shape of the curve in between? Well, it's given by the slope, and the slope is the shear. So the shear starts off at a positive value of 108 and drops down to a positive value of 60. So let's see if I can draw this. So if I actually looked at the slope, it would be 108 to 1, and in this part of the curve, it would be 1 to 60. And then, so I had a constant, had linear. This is a quadratic section. I'll try to draw as best I can. There it is. Okay, now from the last 8 feet, it says the change in the moment is equal to the area in the shear diagram. What's the area in this part of the shear diagram? It's a rectangle. It looks like 60 times 8, that's positive 480. So negative 580 plus 480, hey, negative 100. That worked out. And the curve between these 2 points is defined by the shear value, and the shear value is constant and positive. It has the same slope, 1 to 60. So there's my moment diagram.
So this, maybe the one you did when I was going for the interview was different, but it seems like all the shear diagrams we've been doing are either constant or decreasing. Like, what would it take for the shear to be increasing? Like over, would the distributed load have to be pointing upwards?
What do you mean shear to be increasing?
Your shear graph is dropping left, it's decreasing.
Well, this is the one's a little unusual because it's a cantilever. So using a cantilever, the largest reaction is here, and so you have the biggest shear at the cantilever, and you're going to decrease away from that.
I was just wondering, just because I don't.
If you have a, what do you
like? When would it increase, like going left or right? Like that? Okay.
The shear would go up.
Right, after going across. Like,
that might not. That would kind of depend on the load. I mean, I probably could concoct something.
I was just wondering if it's because it's the distributed loading rate or the applied loads were from underneath.
Well, usually the maximum shear occurs at a connection.
Okay.
So you're going to start probably at a connection. Now, it's possible if I had this problem and I had turned it over, like if I had the same problem but I flipped it around, then you would see. What would you see? You would see it start at 60 and increase up.
Okay.
So that's just direction.